We've talked a lot about electrons and photons as carrying energy and um, controlling the behavior of different materials and stuff like that. Now we're going to turn to that big guy in the middle, the nucleus, which, as it turns out, has a tremendous amount of energy within it. With Marie Curie, um, who won two Nobel Prizes in two different fields, which is sort of astounding. Um, around the beginning of the 20th century, when she won those prizes, people were starting to investigate radioactivity, and it was a bit of a mystery, right? Um, they found that elements were constantly emitting this high energy radiation, which in the way that they were thinking about elements didn't make a whole lot of sense. The energy levels of this radiation was much higher than electromagnetic radiation that we that they were aware was coming from ordinary chemical reactions. Um, and so they were trying to figure out basically where all of that energy is coming from. Um, how can you have an atom that is constantly emitting this really high levels of energy without that, basically without the atom just disappearing, without it being destroyed? How does that work given conservation of energy? And the energy, it turns out, comes from the mass of the material, which is something that in various fields people were starting to explore. Um, that's um, one of Einstein's more famous equations, right? You're all familiar with the E equals mc squared. This is essentially uh, crucial to understanding radioactivity, right? Because what does this mean? Well, C is a constant, a really big constant. And it's saying that the rest energy of a mass, that is the energy that exists in the mass itself, is equal to the mass times this really high constant. So what does that mean? It means that all mass is essentially energy. And so if that mass changes even by a little bit, right, then you're going to have this huge release of energy. So you can take a kilogram of any material and it has a mass energy equivalent to the type of energy that we could produce from a huge amount of coal. So a small amount of mass contains a tremendous amount of energy. So how does this apply to radioactivity? Well, it turns out uranium wasn't violating the conservation of energy. Instead, it was very slowly losing mass. That mass was being converted into energy and then being emitted by that atom. So where is it coming from in the atom? It's coming from the nucleus, which we have a nice little picture of over here. The nucleus is this dense center of an atom, and we sort of grown up. We all know this from high school, right? That protons and neutrons um, are in the nucleus. But I think one of the things that sort of we don't think about too much is these are protons, right? Protons don't like each other. They're trying to expand out from each other, and we're packing, in some cases, tens or even hundreds of protons into a nucleus that is really, really tiny. Okay, so an atom's nucleus has a mass 4,000 times that of its electrons, uh, but is much, much smaller. So it's extremely dense, they're extremely packed together, and yet their electric charges suggest that they would all want to, explode off into and get as far away from each other as they can. Um, we call both the neutrons and protons nucleons, and so I'm including some of the stuff that we're going to be able to talk about later. So just keep that in mind that a nucleon is any particle uh, that is in the nucleus. Um, and an element is defined by the number of protons it has. So its atomic number, which we're going to call Z, um, represents the number of protons, and that generally represents, is a big part of what indicates what the material is, right? Uh, if the atom is balanced, of course, it has the same number of electrons, balanced in a charge sense. If it doesn't, then it becomes some kind of ion, right? Where you have more protons than electrons or more electrons than protons. The mass number is the number of nucleons, so the number of protons plus the number of neutrons. It's an integer, but it's not the same as the mass of the nucleus. It's generally pretty close, but there are some important ways that it's different. And we'll talk about those in a little bit. Two atoms with the same atomic number with a different number of neutrons are called isotopes. And isotopes are the same element, but exhibit different behaviors. So you can have different isotopes of carbon, as you all are well aware. So an ion is an atom that has an unbalanced number of protons and electrons. An isotope is a atom that has a specific number of neutrons, but the same number of protons. So we can pull all of this together and write the notation for an atom, where our mass number is a superscript on the left side. Our atomic number, that is the number of protons, is subscript on the left side. So if we subtract this, right, we can find the number of neutrons. Okay, so if this is 40 and this is 19, then we know we have 21 neutrons there. If it's balanced, we know it has 19 electrons too. So an isotope of carbon with 8 neutrons is written this way, where 6 is our atomic number and 14 is our mass number. And you all, I think, are familiar with all of this, so I'm moving relatively quickly through this. So this one, a lot of this, sometimes you'll actually even see a subscript on the right side that indicates how many neutrons you have. I think we'll stick with this one. You can write this and it's the same thing, C14, because we know, or we can look on the periodic table and find out that carbon's atomic number is 6. So how many neutrons does this have? 8. How many electrons does it have? 6, because it doesn't have a plus or a minus indicating it has a charge.